Sorry about the slightly delayed start, but wherever you might be, welcome back to the Oxford University Scientific Society in week 2 of Trinity Term. This week, we welcome Professor Scott Aaronson from University of Texas at Austin to give a talk on quantum computing. There is no way I can do justice to Professor Aaronson's influence on the field by listing out his past achievements, but I can tell you that I very much look forward to the next hour. As always, do type out your questions in the comments section as the talk goes on. We will collect them for the Q&A session at the very end. With that, I introduce to you our speaker today, Professor Aaronson.
Okay, well, thank you so much for having me here. I've had so many wonderful visits to Oxford over the years, which was a place very involved in the birth of quantum computing decades ago. And today I'm happy that I can at least visit virtually. I decided that the Oxford Scientific Society, deserved something a little bit, more special than my usual canned talk. So I made some handwritten notes for this talk. I'm going to try it as an experiment. I hope you like it. Okay, so what I would like to tell you about is something that's been in the news a lot in recent years, which is this milestone called quantum supremacy. And I want to tell you something about what it means and doesn't mean. Okay, so in order to do that, first I have to tell you something about what is a quantum computer. The good news is that I can do that with very little physics, less than you might expect, because quantum mechanics at its core is really just a certain generalization of the rules of probability. It is almost like an operating system that the rest of physics runs on as application programs. Okay, but you can understand that operating system to a great extent without needing to understand the applications. You can like the behavior of electrons and photons and so forth. You can learn about that later. Okay, so let's start with what is a classical computer. Let's say a deterministic classical computer, one that never makes any random choices. And you could say at a high enough level, at the level that will be relevant for me here, it is very simple to understand. It is just some machine, which we will think about abstractly as being made up of bits. Okay, so and if we're computer scientists, then we don't care that much, how these bits are physically realized, whether they're as voltages or how they're realized in transistors. We just care how they behave. So we can think of the state of a classical computer as a string of n bits, x1 up to xn. And so, of course, the computer then has 2 to the n power possible states. Okay, so there's already this exponentiality in classical computers, but it's only sort of in the possibilities. And of course, really the computer is in one state or the other one. And we can manipulate the state. We can transform it using simple operations that will act on only a few bits at a time. And that will apply some Boolean logic to them. Like, for example, we could replace the first bit by the Boolean AND of the third and the fourth bits. Okay, this is called a logic gate. And this is sort of the building block of our computers, the ones that we're all using right now at the hardware level. Okay, but now, even before we come to quantum computers, there's already something intermediate, something maybe more interesting, which is a probabilistic computer. Okay, so a classical computer, but one that also has the ability to make random choices. That is, to take a bit and set it to be 0 or 1 with equal probabilities, right, to make a non-deterministic choice. Okay, now in our world, it might be that the only source of randomness that is truly fundamental, that is not just a matter of our own ignorance, of the detailed state of the world, is quantum mechanics. Okay, but if a computer were to use quantum mechanics only as a source of random bits, then we would not call that a quantum computer, right? Because that's just a sort of too limited of a use of quantum mechanics. Okay, but we can consider a computer that has access to some true random numbers, and again, a computer that has n bits in its memory. And now something interesting happens, which is if I want to describe the state of that computer, and I don't know the exact random choices that were made, then I will in general have to describe the state by a probability distribution. Okay, so that is, in general, the best I could do is for each of the 2 to the n power possible contents of the computer's memory, I could write down a probability that the memory does have those contents. Okay, so I would get a distribution, call it D, which is really a vector. Okay, it is a list of 2 to the n probabilities, 2 to the n real numbers. So already in classical computing, theoretical computer scientists were very used to dealing with exponentiality, right? The exponentiality of probabilities. Okay, but you could say, well, but all of this is just semantics, right? Because really, if you were to look at your probabilistic computer, you would find that each bit is either 0 or it's 1. Right? You never see a bit being half 0 and half 1. Okay, so really the computer is just in one of these 2 to the n states, and the whole language of probability theory is just a way to encapsulate our own ignorance of what is going on. So you could say that this exponentially large distribution, is not really out there in the world. It is just in our heads. Okay, but be that as it may, if we do represent our knowledge of the computer by this exponentially large distribution, then we can think about how we would update our knowledge. Once we know that something that the computer has done something, has taken a step, has changed its state, and in general, this vector of probabilities can then change to a new vector. And the way it does that is via the rules of probability theory, which basically tell us that we can take this vector and apply a linear transformation to it to get a new vector, as long as that linear transformation always maps a one probability vector to another one. So in other words, as long as it ensures that the probabilities will always add up to 1. Okay, and a linear transformation that does that is called a stochastic transformation. Okay, so now if you understood all of that, then I am ready to tell you what a quantum computer is. Okay, so a quantum computer is at some level almost the same thing as the classical probabilistic computer, except that instead of a vector of 2 to the n real numbers, namely the probabilities, 1 for each possible n-bit string, now we have a vector of 2 to the n complex numbers, which are called amplitudes. Okay, and here I am just with these angle brackets here, which are called Dirac-Ketz. I'm just using the notation that the physicists like to use for vectors. Okay, so we could say that I have a quantum state of my computer, which is traditionally denoted with the Greek letter psi, and it is, as we would say, a superposition over every possible string of n bits, okay, where each string gets some amplitude, that is this alpha sub x. Okay, so each possible string gets an amplitude, and so the state of our computer is given by this vector of 2 to the n power amplitudes, where here n is the number of bits, or in the quantum setting, we call them quantum bits or qubits. Okay, a qubit is just a bit that can have some amplitude for being 0 and some other amplitude for being 1. So it can be in a superposition of the 0 state and the 1 state. Okay, and the amplitudes have to be normalized, which means that if I add up the squares of the absolute values of all of these complex numbers, then I have to get 1. Okay, and so we could say that this psi, this quantum state, what it really is a 2 to the n dimensional unit vector of complex numbers. Okay, and this is the central thing that quantum mechanics says about the world, right? That the way to describe, a physical system or the state of a physical system is using these vectors of amplitudes, these vectors of complex numbers, one for each possible configuration that you could see your system in. Okay, so but I haven't really told you what this means, right? I mean, now I've told you, this is the core of quantum mechanics, right? Everything else, you'll ever hear about quantum mechanics is just different applications and implications of this one change that we're making to the rules of probability. Okay, that we are replacing probabilities by these complex numbers, these amplitudes. In everyday life, you would never talk about a negative 30% chance of something happening, much less an I% chance or a complex number chance. But in quantum mechanics, we use these complex numbers, which are going to be very closely related to probabilities, but which are not probabilities. Okay, so now how does this rather abstract picture of these vectors of amplitudes, how does it connect to what we can actually do or observe? So if you are to look at your quantum state and sort of ask it, like make a measurement and say, what string do I have? Then just like in the case of classical probability, you are not going to see this whole vector, right? You never directly see an amplitude, okay? All you're going to see is some particular string. That is, for each qubit that you measure, to ask it whether it is 0 or 1, it will tell you one or the other. It will tell you that it's 0 or that it's 1. And the rule is that you will see a string of bits x with probability equal to the squared absolute value of the amplitude of x. This is why these squares had to add up to 1, so that the probabilities would. And furthermore, once you make a measurement, then famously the quantum state collapses to whichever outcome you saw. Okay, so if you make a measurement and you see that the let's say some qubit is 0, then nature has made up its mind that qubit shall be 0. If you look again, nothing having happened in the meantime, then that qubit will still be 0. And all of the other information about the amplitudes is now gone. It's inaccessible to you forever. Okay, so why is this not just a fancy language for saying, well, we don't know whether our bits are zeros or ones, and then we look at them and then we do know, right? Well, the reason it's more interesting than that is that you can do other things to a quantum state besides just measuring it. In particular, you can apply what is called a unitary transformation. Okay? And this is the quantum version of a stochastic transformation that I mentioned before. It is just any linear transformation of the vector of amplitudes that preserves the property that the probabilities add up to 1. Okay, so any a linear transformation that maps unit vectors to unit vectors, and this is called a unitary transformation. Okay, now these unitary transformations can produce what's called interference of amplitudes, where, for example, a positive and a negative amplitude would cancel each other out and produce a sum of 0. Now, this is sort of the central phenomenon of quantum mechanics. Okay, this interference is the central effect that sort of tells us that we are dealing with a quantum system, or tells us that the world is quantum mechanical to begin with. That these amplitudes were really there. Okay, so here's a very simple example. I could have a vector of amplitudes like a 1 over root 2, 1 over root 2. Okay, so this is called an equal superposition of the 0 state and the 1 state. This component representing the amplitude of 0, this component representing the amplitude of 1. I could then take that superposition, that vector of amplitudes, and apply to it some 2 by 2 unitary matrix, such as this matrix right here, which basically just corresponds to a 45-degree counterclockwise rotation in the plane. So if I think of my original vector as pointing like this, then it's just going to rotate my vector by 45 degrees and give me this vector here, 0, 1. So which means now my qubit is definitely in the state 1. Okay, and it has 0 amplitude for being in the state 0. So what has happened here? Well, if you think about it, there were contributions to the amplitude of the state 0. Okay, but one of those contributions was 1 over root 2 times 1 over root 2, so it was positive. The other contribution to the amplitude of the state 0 was minus 1 over root 2 times 1 over root 2, so it was negative. Okay, and those two contributions canceled each other out, producing a total amplitude of 0 on the state 0. So there were two ways for an event to happen, but because their amplitudes had opposite signs, they canceled each other out, and that event never happened at all. Okay, this is quantum interference. Okay, the famous experiment that illustrates this as part of the nature of the world is the double slit experiment. Richard Feynman used to say that all of quantum mechanics is contained in this one experiment, and this is the thing where you shoot a particle like a photon, so let's say just one of them at a time, at a screen with two small slits in it. And then you look at where the photon ends up on a second screen behind it. And what you find is, well, first of all, the result is probabilistic. So you could repeat with exactly the same initial conditions and see sometimes the photon will land in one spot and sometimes in another spot. Okay, now that by itself is not the surprising part. The surprising part is the way we have to calculate the probabilities. Okay, so what we find is that there are certain spots on the second screen where the photon just never wants to appear. It just doesn't appear there. And yet, if we closed one of the slits, then the photon could appear in those spots. Okay, so to say that again, by decreasing the number of paths that the photon could take to get to a certain spot, we can increase the chance that it gets to that spot. Okay, this is the part that violates the rules of conventional probability theory. But it is very easy to explain once we understand that that the world is quantum mechanical and that the photon can have a superposition with some amplitude to go this way and some other amplitude to go this way. And then what can happen is that if one of the paths leading the photon to this spot has a positive amplitude, say alpha, and the other path leading there has a negative amplitude, say minus alpha, then these two amplitudes can cancel each other out, producing a total amplitude of 0. Whereas if I closed one of the slits, now the amplitude is alpha or it's minus alpha, and in either case, its squared absolute value is now a positive number, and now the photon can appear there. Okay, so now this has tremendous philosophical implications. Ones that people have been arguing about for a century now. Okay, but for this talk, the main one is that because of the phenomenon of interference, because these amplitudes, these 2 to the n amplitudes, representing the possible states of our n qubits, can actually interfere. They can cancel each other out. We don't have the option of saying that, well, before we looked, our system, our bits were really in one, definite state of 0 or 1, right? That they were really some particular string. No, we have to keep track of this entire vector of amplitudes, because even though we will never see the amplitudes, we will need them to calculate the probabilities of the various possible strings of 0s and 1s that we will see when we look. Okay, and so this seems to force us to admit that that this entire vector of an exponential number of amplitudes was in some sense really there. It was out there in the world. It was not just in our heads. And this is a staggering claim about reality. I think it took many decades for it to sink into people, just how staggering it was, even though Schrodinger, already noted it in his original paper on wave mechanics in 1926. What this exponentiality means is that, just to keep track of the state of, let's say, 1,000 particles that are interacting with each other, it seems that nature has to have some scratch paper that we never directly see. And on that scratch paper, it has to write a list of 2 to the 1,000 power complex numbers, 2 to the 1,000 power parameters, which happens to be much, much more than the number of subatomic particles in the entire observable universe, which is only about 10 to the 85 power. Okay, so 2 to the 1,000 complex numbers, that in some sense are really there, or at least are needed to describe the state of the system, to predict the probabilities of the results that we will see when we look. And whenever anything is done to those 1,000 particles, then we're saying that nature has to cross off all of those 2 to the 1,000 complex numbers and replace them by new complex numbers. Okay, so that is a staggering amount of work for nature to be going to, just to sort of produce the world, to sort of do the computations that underlie the world. It is much, much more than even the already enormous amount that one might have thought if one didn't know about quantum mechanics. So chemists and physicists have known about this exponentiality for a long time, but they've known it mostly as a practical problem. That if you are trying to simulate quantum mechanics with a conventional computer, to learn about the behavior of some molecule or some material, then you need to keep track of these exponentially many parameters, and you can often invent clever shortcuts that will avoid it. But in general, you might need a gigantic supercomputer, just to simulate a very small molecule. And indeed, that's exactly what people do today. They use some of the most powerful computers on the planet to try to simulate quantum mechanics, and there are severe limits to what they can do even then. Okay, so it was not until the early 1980s that a few physicists, most famously Richard Feynman and Oxford's David Deutsch, had the remarkable idea that if nature is giving us this computational lemon, why don't we make lemonade out of it? Or in other words, why don't we build computers that themselves would be made of qubits? That themselves would be able to take advantage of this exponential proliferation of amplitudes, of interference among all of those amplitudes. Of course, they faced the question, supposing you built such a computer, what would it be good for? And they didn't really have an answer to that question other than, well, it would be good for simulating quantum mechanics itself. Which is indeed a huge application, maybe still today the most important application that we know. Okay, but it took another decade or so before anyone for people to really figure out what other tasks a quantum computer could be useful for, and I will say something about that later. Okay, but what this talk is mainly about is this milestone that was achieved or claimed to be achieved just a couple of years ago. Shortly before COVID shut down the world, and this is what's called quantum supremacy. Now, this is a term that was coined by the physicist John Preskill in 2012. Not everyone likes the term, but it's sort of stuck, so I will use it in this talk. And what Preskill was referring to was just the first actual experiments that would convincingly exploit this exponentiality in amplitudes, that is inherent to quantum mechanics, in order to actually solve some well-defined computational problem, so some benchmark problem, and actually solve it much faster than we know how to solve the same problem with any existing classical computer. Okay, so for the context is, for 25 years now, there have been small-scale experimental demonstrations of quantum computers. For a long time, they involved just 2 or 3 qubits. So superpositions involving 4 amplitudes or 8 amplitudes. And these were interesting proofs of concept. Interesting experimental systems. But they were not doing anything that your smartphone would break the slightest sweat to simulate. Okay, they were not outperforming a classical computer. If you want to outperform a classical computer, then what it seems is that at the least you would want maybe about 50 qubits, because then a classical simulation might take 2 to the 50th power time. Now that is causing 2 to the 50th power would cause the biggest supercomputers now on Earth to at least to break a sweat. Okay, so quantum supremacy, you should think of as targeting a roughly that scale of problems. Now, you may notice that I didn't say anything about solving a useful problem. Okay, so that is not part of this this milestone. The problem that the quantum computer is solving could be a completely useless and contrived benchmark. That is fine, just as long as it is mathematically well defined, so that we can judge whether the quantum computer has succeeded or failed at the task. Okay, and you should think of the Wright brothers airplane, let's say, or Enrico Fermi's nuclear chain reaction, right? These were not useful in and of themselves. They were built in order to prove a point. that a certain technology can work, or can give you an advantage over what you could have done without it. Okay, so now the question becomes, how should we actually achieve quantum supremacy? What would a convincing demonstration of quantum supremacy consist of? Now, since the mid-1990s, we have known a gold standard for a convincing quantum supremacy demonstration. And this is the famous algorithm of Peter Shor, a Shor's algorithm for factoring numbers. This was the discovery in the mid-90s that really made the wider world excited about quantum computing in the first place, or that sort of put it on the wider intellectual map. Okay, what Shor discovered was that if you built a full programmable quantum computer, and you had complete control over, let's say, thousands of qubits, then you could, there is an algorithm, that would exploit this interference that I talked about before to find the prime factors of a composite number very, very quickly. In particular, you could factor an n-bit number, an n-digit number, in a number of steps that scales only about like n squared. Okay, whereas the best known classical algorithm for factoring uses a number of steps that scales exponentially with the cube root of n, to be precise. So this is an exponential speed up over the best known classical algorithm. And not only that, it's a speed up that actually matters enormously, because for better or worse, most of the public key encryption that we currently use to protect the internet. So the encryption that is used whenever you use your web browser, and there is a padlock icon, and there is HTTPS, and you are sending your credit card number over the web. The encryption is based on the belief that factoring and a few other closely related problems in number theory are hard, take an astronomical amount of time to solve. What Shor showed is that once we can build fully programmable quantum computers, then that is no longer true. Then all of that existing encryption is broken. Okay, now I should clarify that not all possible encryption would be broken, and in fact there is a big move today to try to shift people to different encryption systems that we believe to be quantum resistant. Okay, and we already have good candidates for that. Just that those are not the systems that are widely used today. Okay, so but now for the purpose of quantum supremacy, what's relevant is that not only is this a very dramatic demonstration of the power of a quantum computer, to quickly find factors, but once the factors have been found, it is very, very easy for any skeptic to go and check. Right, they can multiply the factors together, see that they work. There are even known algorithms to check that the factors are really prime. Okay, so it's easy to verify, that the quantum computer did what it was supposed to do. Okay, so this, if you could demonstrate Shor's algorithm to factor, say, a 2,000-digit number, then there would be very little arguing about it. Like you would. Clearly quantum supremacy has then been achieved. Okay, but there are also a couple of drawbacks. Now, the main practical drawback is that we are nowhere close to building the kind of quantum computer that would be able to run Shor's algorithm and get an advantage from it. It seems that if you want to run Shor's algorithm with, let's say, thousands of qubits, you're going to need to protect the qubits from interaction with their environment. That's going to require something called quantum error correction, or quantum fault tolerance. And as soon as you need that, it tends to blow up the number of qubits that you need by factors of thousands. Okay, at least using any of the error correction methods that we know today. So at that point, you're talking about a quantum computer with millions, or even hundreds of millions of qubits. You know, it might you might need equipment that fills a building. You know, it might need days or weeks to do the factoring. So maybe the NSA or the GCHQ, you know, might, you know, it might be worth it for them to actually build this, but I certainly don't think it's going to happen anytime soon. Right. Now, second, a more theoretical issue is that no one actually knows whether the prime factorization problem is hard for classical computers. You know, we believe it enough that we base our internet commerce on that belief. But, you know, as far as computer science is concerned, you know, if there were a fast classical algorithm for factoring, it wouldn't really have any dramatic consequences that we know of for anything else, right? So, you know, and there are mathematicians who believe that such an algorithm, you know, plausibly exists. And, you know, if it does, then Shor's algorithm would not be getting an exponential speed up over what you could do with a classical computer. Okay, so a decade ago, I and others were thinking about these issues, and there's some sort of ideas coalesced together, and we ended up proposing a much more direct route to achieve quantum supremacy than, you know, via, say, a full quantum computer running Shor's algorithm. And the route that we proposed was to look at what are called sampling problems. These are problems where there is not a single right answer, as there is for factoring. Okay, the desired answer is a sample from a probability distribution over n-bit strings. Okay, and our goal was just to find some distribution over strings that is easy to generate a sample from with a quantum computer, hard to generate a sample from with a classical computer. Okay, and now the point is that once you change the goal in this way, then you find two things that are really nice. The first is that there are such distributions that could be sampled even by very rudimentary quantum computers. Okay, so instead of needing, you know, millions of qubits and full error correction and so forth, there are probability distributions that plausibly, you know, one could sample from even using only 50 or 100 noisy qubits. Okay, and now you're, you know, the experimentalists become, you know, much more optimistic that, well, you know, maybe we can actually do this, you know, in a matter of years rather than decades. Now, the second thing is that we could give extremely strong theoretical evidence that there is not going to be a fast classical algorithm to do the same thing. Okay, you know, it's still not a proof, right? We just don't know how to prove these sorts of statements in theoretical computer science. But what we can show is that if there were a fast method for a classical computer to generate samples from these same distributions, then rather dramatic things would happen to the hierarchy of computational complexity theory. An example is something called the collapse of the polynomial hierarchy. I'm not going to explain what that means, but if you've heard of the P versus NP problem, you know, the collapse of the polynomial hierarchy would be almost as dramatic, I would say, as a proof that P equaled NP. Okay, it's wouldn't have quite as many consequences for the real world, but, you know, in the theoretical world of computer science, it would be almost as surprising. And we could give examples of quantumly sampleable distributions where if you could sample them classically using an amount of time that was polynomial, there's a number of steps that grew like n, the number of bits raised to some fixed power, then the polynomial hierarchy provably would collapse. And this is, close to the strongest evidence that a problem is hard that one hopes for in the current state of theoretical computer science. Now, admittedly, once you introduce noise into the experiment, you introduce all the realistic issues like photons getting lost, your device is being not calibrated, then it becomes harder to say, well, could a classical computer spoof the noisy version of the experiment? Then if you want that to be hard too, then you have to make some, you have to stick your neck out further, make some stronger conjectures about what is hard for classical computers. Okay, but those stronger conjectures look very plausible to us as well. Okay, so an example of such a proposal was what my student Alex Arkhipov and I called boson sampling. This is where you just generate some photons, you send them through a sequence of beam splitters, and then you just measure where all of the photons ended up. So that's all you do. The task is just to generate a sample from what quantum mechanics predicts would be the distribution over how many photons would appear in each output port. And now the point is, there are and the beam splitters can just be chosen randomly. Okay, so you could think of it as you are doing a random sequence of operations to your quantum state of, let's say 50 or 100 photons. And now there is an exponential number of possible outputs. Okay, so you could see 3 photons here, 0 photons here, 5 photons there, or you could see 2 there, 1 here, and so forth. Okay, so there's a combinatorial explosion of possible output states. You'll probably never see the same output twice in the whole, no matter how often you run your experiment. But not all of the outputs are equally likely. And this is really the crucial point. Okay, the amplitude for each output is a sum of exponentially many contributions. And those contributions will look more or less random, just like random complex, let's say random complex numbers with a mean of 0. And so, the complex numbers will mostly cancel each other out because, they're just pointing in every possible direction in the complex plane. But the cancellation will not be perfect. There will still be a little residue that's left over. And that will determine the probability that you see this particular state, the size of that residue. Okay, and the residue that's left over after all this cancellation will be a little bit bigger for some of the outputs than it will be for others, just randomly. Okay, but now the point is, if we've got a powerful enough classical computer, and if the classical computer knows the complete sequence of operations that the quantum computer was applying, then it can simulate this entire setup, and it could predict which outcomes are likelier than others. Okay, so now when we run the actual experiment and we see the even just a small number of outputs, we can do statistics on them. We can say, are we preferentially seeing the outputs that were predicted by our classical computer to be the more likely ones? Okay, and that is exactly what is done in these quantum supremacy experiments. Okay, so this brings me to the actual experiments that were announced over the past couple of years. Okay, so the first announcement of quantum supremacy was by the group of Google in their lab in Santa Barbara in fall of 2019. So they had been working on this for about 5 years. And 2 years ago, they announced that they published a paper in Nature announcing that they believed they had done it. What they did was that they built a programmable chip with 53 qubits. They used a technology called superconducting qubits. Their chip is called Sycamore. If you're wondering why 53 qubits, well, apparently they built 54, and one of them didn't work. Okay, but they're arranged roughly in a rectangular grid on the chip, where each qubit can talk to its neighbors. The chip is placed into a dilution refrigerator, which if you see a picture of one, it looks kind of like an upside down wedding cake, and it's cooled to about 10 millikelvin. So just slightly above absolute zero. That is what you need to cause the chip to superconduct, which is what allows these bits, these currents flowing around these little wires to behave as qubits at all, to behave quantum mechanically. Okay, even then, even at this ultra low temperature, you're still only maintaining a quantum superposition state for a very short time, for about 40 microseconds. Okay, but that is enough to already do an interesting quantum computation on the qubit. So what they do is, within that time, they're able to do about 1,000 operations on the 53 qubits, each one acting on one or two of the qubits. Yeah, the operations are arranged into 20 layers. Now, this entire chip was specifically designed just to demonstrate quantum supremacy, along the lines that we had proposed in 2011 or so, based on sampling problems. By sampling from some probability distribution over, in this case, strings of 53 bits, where the idea is that this chip can very quickly generate a sample from that distribution, on demand, in 40 microseconds. But if you wanted to sample from that same distribution with a classical computer, then the best known algorithms might need a number of steps that's like 2 to the 53 power, which is about 9 quadrillion. Okay, so that is the separation that they're going for. Okay, so they actually built all of this. They had a team of 75 people. I think it was $100 million or so, and they were able to build a chip where there is a lot of noise in the system, right? Because the qubits are not error corrected. Okay, so what you see each time you take a sample is like 99.8% just uniformly random noise, just completely random zeros and ones, which of course you would not have needed a quantum computer to generate, which is not interesting. Okay, but you have at like the level of 0.2%, you have a signal. You have a bias where some output strings are a little bit likelier than others. And now, because the chip is so fast, in 3 minutes, they were able to take several million independent samples. And that is enough to extract a signal from that level of noise. So they applied a statistical test to the millions of samples that they collected, which they called the linear cross entropy benchmark, or LXEB. It just involves checking a certain inequality, involving the ideal probabilities of the samples that were observed. In particular, just summing up all of those probabilities and checking whether or not the sum exceeds a certain threshold. Where I've underlined this number here. If you just had if you were just picking samples randomly with no quantum computer at all, then this number should be 1. If you had a perfect quantum computer with no noise, then this number should be 2. Okay, but if this number is anything above 1, then that is the signal that you were that quantum interference was actually happening, was boosting the probabilities of certain outputs in a way that we think is hard to simulate with a classical computer. Okay, and as you can see, they find that signal. Okay, now my students Li Ji Chen, Sam Gunn, and I had given theoretical evidence that under reasonable assumptions, any classical algorithm, even that just simply spoofs this test, the test that Google applied to its outputs, should need an amount of time that increases exponentially with the number of qubits. At least if there is a faster classical way to spoof the results, then that would have some surprising implications. Okay, now just 5 months ago, the group of Chaoyang Liu and Jianwei Pan in Hefei, China, announced a second achievement of quantum supremacy. And that one was using a completely different hardware platform. It was using our original proposal of boson sampling. So they literally just built a gigantic optical table into which they could pass an average of 50 photons through a network of hundreds of beam splitters, and then measure where the photons end up. So they have about 10 to the 30th power possible output states, which is more than in Google's experiment, which was like 10 to the 16 power. If none of the photons were lost, if the experiment were really done perfectly, then we expect that it would take something like 2 to the 50th steps to spoof the results of the experiment using a classical computer. There is still a debate ongoing about this experiment, which has to do with partly with the fact that a large fraction of the photons get lost in the beam splitter network and are never detected. It is possible that the photon losses and other imperfections could allow a shortcut to simulating the experiment with a classical computer. Which could then negate the claim of quantum supremacy. We don't really know yet. People are still working on it, but at any rate, they've outperformed any of the classical simulations that they or others have so far been able to find. Okay, so what I want to do in the remaining time is mostly briefly describe some of the objections to these sampling-based quantum supremacy experiments that tend to recur, and make some comments on these objections. I think that some of the objections are more serious than others. Okay, so the first objection is one that the mathematician Richard Borchards recently offered on YouTube, and I wrote a blog post responding to it. And he sort of parodied quantum supremacy with the example of a teapot. He said, look, if I took a teapot and I just smashed it on the floor, that would achieve supremacy over classical computers for the task of simulating a teapot that is smashed on the floor. But clearly that is not interesting. Right? Clearly, it's not interesting to just point to any complicated physical system and say, well, it achieves supremacy at the task of simulating itself. So, why is quantum supremacy anything more interesting than that? Now, my opinion is that this is just a simple misunderstanding of what the quantum supremacy experiments are. Okay, with the sampling-based quantum supremacy experiments, what you do is you don't just point to a device like a chip or a beam splitter network and say simulate whatever that does. That is not what we're doing, right? We're saying here is a mathematical specification of a problem to be solved, of a distribution to be sampled. Okay, now it just so happens to be one that is designed with that device in mind, but no matter, right? Once we have specified the distribution, then a classical computer, has all of the data that it needs to also generate samples. The quantum computer can generate samples, but logically it could also fail to do so, right? I like to say that in order for a physical object to count as a computer, it has to be at least logically possible for that object to output a wrong answer, right? There has to be some external standard against which you are comparing it. Okay, and that is true with the quantum supremacy experiments. A classical computer can and does check the work of the quantum computer. It is just that it needs exponentially more time to do so. Now, that would not be the case with a teapot, because with a teapot, a classical computer just would not know the detailed microscopic state of all of the atoms in the teapot and the atoms of the air and so forth. What would be fair would be to ask your classical computer to just sample from a probability distribution over all the plausible evolutions of a teapot that is dropped to the ground. But that is something that a classical computer can do. Okay, so I don't think that a teapot actually achieves supremacy for that task. There is not an exponential advantage as you see when you're actually exploiting quantum mechanics. Okay, second response is simply, well, quantum supremacy experiments are not interesting because they are useless. They are only demonstrating a speed up, but not to solve any problem that anyone independently cares about. All right, well, a first response to that is, so what? We said from the beginning, that, this is just to prove a point. And, if someone promised you more than that, well, then, you shouldn't have listened to that person, right? This is a step, in a long road to getting devices that we hope will, ultimately will actually do useful problems. But, let's approach things like scientists. Let's, establish the truth of the reality of the phenomenon in question, before we try to make money off of it, right? But now, recently, a second response has emerged. So a few years ago, I realized that these sampling-based quantum supremacy experiments actually do have at least one potential application. Namely, if the experiment works, if you generate samples that pass the statistical test, like this linear cross-entropy benchmark, then not only do you have some sort of certification that a quantum computer must have been used to produce those samples, you have some sort of cryptographic guarantee that even a quantum computer could only have produced those samples randomly. Okay, it could not have done so in a secretly deterministic way. We just, we expect that would have been exponentially more difficult. Okay, and so now you have a sort of cryptographic guarantee of randomness. And now that could be useful for all sorts of applications. A prominent example being what are called proof-of-stake cryptocurrencies, such as the next generation Ethereum, where you need to constantly run a lottery to decide who gets to add the next block to your blockchain. So the decision has to be made randomly, and everyone has to trust that it really was random, because billions of dollars are riding on that, or pounds. There are many ways that you could imagine getting sort of certifiable randomness, but these quantum supremacy experiments are one possible way to do that, and Google has actually been exploring that, has been trying to implement my protocol. Okay, now the third objection is, well, the entire point of quantum computers was supposed to be to outperform classical computers in asymptotic scaling behavior. That is, to solve problems with polynomial scaling, in n, that classically would have required exponential scaling with n. Okay, but there's something fishy about the quantum supremacy experiments, at least the existing ones, because they are not scalable, right? Because the qubits are not error corrected, we don't expect to be able to scale these experiments beyond, let's say, a few hundred qubits at the most. Okay, so what is going on with that? And I admit that this is true, right? We do not yet have scalable quantum computers. If we did, we would just run Shor's factoring algorithm and be done with it. But at the same time, I would say to a skeptic, well, can you explain the success of these experiments, or the outcomes of these experiments, without needing to invoke, the reality of this vector of 10 of quadrillions of amplitudes, or of 2 to the 50th amplitudes? If you can't, then I would say that one of the main claims of quantum computation has now been empirically demonstrated. It has now been demonstrated that you can harness this exponential growth of in the number of amplitudes in order to solve computational problems faster. And it remains to be shown that you can error correct the qubits in order to truly scale to thousands of qubits. But this really was one of the main points at issue, and to settle that point is a really big deal. Okay, now the fourth response, or sort of fourth objection, is, okay, but how do we know that these quantum supremacy experiments were really doing something that was hard for a classical computer, right? Maybe they can be simulated classically much faster than the proponents believe. So my response is, well, that is indeed a really big worry. And in fact, after Google's quantum supremacy claim came out, there were rebuttals by IBM, which is Google's main competitor in superconducting qubits, which said, well, we don't think Google has achieved quantum supremacy. We could, and they sketched how they could, they thought that they could simulate the results. Admittedly, though, they using the largest supercomputer currently on the planet, which is called Summit at Oak Ridge National Lab, and which has 250 petabytes of hard disk space. And their proposal was to just write the entire list of 9 quadrillion amplitudes to hard disk, do the simulation that way. And they said it would take maybe 3 days. Alibaba had a different way to simulate Google's experiment using what are called tensor networks. Okay, but it's important to realize that even while the classical simulation methods improve, and I think it's now shown that using a reasonable supercomputer, yes, you could simulate the Google experiment in a matter of days or weeks. So the experiment is still faster, but the speed up is only by a factor of thousands. It's not by millions or billions. But on the other hand, the quantum computers are going to continue to improve extremely rapidly, right? Even while the classical simulations also improve, right? So the question is, well, who is going to win this race? Well, now the important point is that no classical simulation method is known yet that really breaches the exponential barrier. That sort of does not have exponential scaling. And we've given some theoretical evidence that is unlikely. And as long as that remains the case, then I would say that quantum computers are predictably going to win this race decisively, and do so within a matter of only a few years. It's sort of like the Kasparov versus Deep Blue chess competition in the 90s. Like if it's a close fight in a certain year between the best human and the best computer, then you can reliably predict that a couple of years afterward, it will no longer be a close fight. The computer will just have complete dominance. And that's very much the situation with quantum supremacy, unless something happens, unless some new discovery is made that would allow classical computers to breach this exponential barrier. Now, the fifth objection is, well, with existing quantum supremacy experiments, it's actually just as hard for a classical computer to verify the quantum computer's results as it is to simulate those results. And this means that if you really go completely beyond what a classical computer could simulate at all, as let's suppose if Google had used 100 qubits or 200 qubits instead of only 53 qubits, right? And if they really went completely beyond what a classical computer could do, then they would also be completely beyond what a classical computer could check. So they couldn't even prove that it worked. So how do we get to say that this is quantum supremacy? So the response to that is, well, what one does is one demands that the quantum computer produce its outputs very quickly, like let's say in a few seconds or a few minutes, and one can then use the biggest supercomputers in the world to verify the results at leisure. The classical computer can take weeks or months to do the verification, and you can use 1 million parallel processors, let's say, to help you verify what just the single quantum computer had done. So you can demonstrate that there is a large gap in performance in that way. Having said that, yes, I think that this is maybe the biggest drawback of the quantum supremacy experiments as they stand. One of the biggest open problems in this area is, how can we get an experiment that is both realizable, using near-term quantum computers, and that achieves quantum supremacy, and where the results can be easily verified using a classical computer. There's been some progress on that, but we don't know how to do it yet. That's a huge challenge. Okay, now one unfortunate effect of the announcement of quantum supremacy is that it has really turbocharged a lot of the irresponsible hype, that there's been around quantum computing. And that hype has been there for decades. In fact, one of the main roles of my blog for the past 15 years has been to try to counter the irresponsible hype around the practical applications of quantum computers, changing everything. But now quantum supremacy, I think partly just because of the term, just because of how awesome it sounds or whatever, it is really kicked the hypesters into overdrive. And so they if you read, I would say, most popular articles about this field, they will give a very misleading picture of what we expect quantum computers to be able to do, right? And they will say things like, well, unlike a classical computer, which could just try, each possible answer one at a time, a quantum computer could just try every possible answer in parallel, as in this picture here. And the trouble is they give the impression that then the quantum computer could just somehow instantly pick the best answer. Now, if this was true, then quantum computers would give speed ups not merely for factoring or quantum simulation or a few other special problems, right? They would completely revolutionize optimization and machine learning and everything like that. They could solve the so-called NP-complete problems in polynomial time. Okay, now it is really crucial to understand that we do not expect quantum computers to be able to do that. Okay, and this is not even controversial within the field, but there is this sort of wall of obfuscation that prevents this message from getting out to the wider world. But since this is my talk, I can tell you the truth. Okay, the problem is that, well, with a quantum computer, yes, you can create an equal superposition over all the possible solutions to your problem, even if there were exponentially many of them. That is even an easy thing to do with a quantum computer. But for a computer to be useful, at some point you have to measure it. You have to look at it and see an output. And if you just measured the state, if you just measured an equal superposition over all of the answers, not having done anything else, then all you're going to see will be a uniformly random answer. And if you just wanted a random answer, you could have picked one yourself with a lot less trouble, right? So the entire hope of getting a speed up from a quantum computer is to exploit the way that the amplitudes, being complex numbers, work differently from probabilities. In particular, it is to exploit interference, right? With every quantum algorithm, like Shor's factoring algorithm and all of the rest, the idea is to choreograph a pattern of interference such that for each wrong answer, each one you don't want to see, some paths leading to it have positive amplitudes and others have negative amplitudes, let's say, so that on the whole, they cancel each other out. Whereas the amplitudes leading to the correct answer should reinforce each other. Okay, if you can arrange that, then you will see the right answer with a high probability, right? The quantum supremacy experiments did this in a very crude way, right? With just a little bit of, destructive and constructive interference. Shor's algorithm would do it in an incredibly well-controlled way, concentrating almost all of the amplitude on a tiny subset of the answers. Okay, but this is a very weird ability, right? It is weirder than any science fiction writer would have had the imagination to invent, I think. And it is, nature is giving us this very strange hammer of interference where, we then have to find the special nails that this hammer can hit, right? The main way that people go astray in hyping quantum computing is that they ignore all of that. Okay, they pretend that a quantum computer is just a general purpose oracle or this godlike machine that could speed up anything. Okay, and they say, well, quantum computers, are going to revolutionize, industrial optimization problems and deep learning and basically anything that sounds good, right? Where in many cases, those of us in this field, we have no idea what quantum algorithms there actually are that would be able to achieve those speed ups that are promised. And yet, hundreds of millions or billions of dollars of venture capital have been raised based on investors making these promises that I have no idea what they're based on. Okay, so the known applications of quantum computers. Well, maybe, as I said, the most important is maybe simulating quantum mechanics itself. So in order to understand chemical reactions, possibly design new drugs, design new solar cells or materials, high temperature superconductors. We expect big quantum speedups there. It is even possible that we could see some advantages using noisy, non-error corrected quantum or only partially error corrected quantum computers in the relatively near term. Okay, so that's an exciting prospect. Secondly, of course, is breaking cryptography, where quantum computers do promise a clear exponential speedup, but not in the near future. That will really require a full error-corrected quantum computer. Now, thirdly, for all of these problems like search, optimization, Monte Carlo estimation, so a huge number of industrially relevant problems, machine learning problems, there is a quantum algorithm called Grover's algorithm that can typically solve such problems in about the square root of the number of steps that a classical computer would need. So that has an enormous range of applications, but it will be a very, very long time, probably even longer than for Shor's algorithm, until you could actually see an advantage with Grover's algorithm, okay? Because not only will you need a full error-corrected quantum computer, but because the advantage here is more modest, it is square root rather than exponential, the crossover point where you start outperforming a classical computer is then pushed much further into the future. And then fourthly, there are all sorts of quantum algorithms that people have proposed where we don't really know how well they're going to perform in practice, and where we might need to actually build the quantum computer and try them out before we really know, whether these can outperform the best things that we could do using classical computers. And into this category, I would put what's called adiabatic optimization, also most quantum algorithms for machine learning problems. And you see huge numbers of confident claims about the revolutionary impacts that quantum computers are going to have based on these algorithms. And almost all of it, the way I would put it is that it is based on an axiom of optimism. It is based on the idea that, well, if experts can't prove that there's not a huge quantum speed up to be had there, then you just get to proceed on the assumption that there is such a speed up. I feel like we ought to have a higher standard than that. Okay, so what I'd like to end with is what does quantum supremacy mean for our understanding of the world? I guess I promised to say something about that in my abstract. So famously, Hugh Everett in the 50s, and more recently David Deutsch and others, have forcefully argued that quantum mechanics just seems to logically entail the physical reality of exponentially many parallel universes. This is what's called the many worlds interpretation of quantum mechanics. And the idea here is that if you just follow the evolution of a quantum state, of the vector of amplitudes as it undergoes unitary evolution, there is no obvious place for it to ever stop. Even when you make a measurement, and traditionally we would say that collapses the state to one outcome or the other. But even that too could be modeled as just another unitary transformation, another interaction where you yourself would become correlated or entangled with the quantum system that you are measuring. So that is a very simple, parsimonious, elegant picture. The one issue is that it leads to this view where the world is constantly branching into different components, each of which has an amplitude. And maybe we only experience one of the components, but there would be nothing to make the other components go away, or to make these parallel worlds, if you like, not exist. So even after we, if and when we do get truly scalable, practical quantum computers, I expect people to continue to debate about these questions. Are there really parallel copies of you where your life turned out differently, or parallel worlds where we don't have COVID, or where world events have happened differently? Okay, but I think if anyone thinks that the world does not provide this computational resource of exponentially many amplitudes, like the ball is now, given the quantum supremacy experiments, I think the ball is in their court to explain how that could be. All right, so with that, thank you for your attention, and I apologize for going over time, but I'm happy to take any questions.
Thank you very much. This was really, really interesting, and I really appreciated your discussion about when are these things going to be actually available. So I think we can go now for the question. So I have a lot of questions myself, but let's give some priority to the audience. So the first question is, so do you envisage that in the future people will have commercial personal quantum computers in the same way that we now have PCs? And will they completely sort of supersede classical computers?
I don't expect that to ever happen, and I will tell you exactly why. Okay, because you don't need a quantum computer to play Angry Birds, or to check your email, or to do 99% of the things that we want to use computers for. And furthermore, when you do need a quantum computer, the wonderful thing is that we now have this internet, right? And so, you can simply make a quantum computer available as a cloud resource, right? And this is the model that, Google and IBM and various startup companies are already pursuing right now, right? Where, you could just submit tasks to, a quantum computer, for those specialized applications where it could provide you some benefit, and you consult it over the internet, right? So it's always risky to make these predictions, right? I'm aware that it was predicted decades ago that there was absolutely no reason why anyone needs a computer in their home, right? And that is often ridiculed today as one of the wrongest predictions in history. But actually, I think if you look at what Ken Olsen, who made that prediction, was actually thinking, he was really thinking about what today we would call the cloud, right? That you could just have the computation be centralized and then have everyone access it through a network. And the world really is moving to that model. So you could say, he was really just ahead of his time, right? And I think that, quantum computing, for the foreseeable future, it makes by far the most sense to have it be provided as a cloud resource. Once it usefully works at all.
Fair enough. That's a very interesting thought. Let's see what happens in the next 20 years. Aaronson, can you send us the next question? I think we still have time for another one or two questions, perhaps. So this question comes from Arthur from the audience.
Okay.
It says, given classical approximation algorithms, readily accessible classical resources, enabling a particular runtime, error correction, etc., would you expect a square root speedup on NP hard optimization problems?
To actually have any practical applications? Yeah, it's a very good question. Not for the near future. I would be very surprised to see that in the next few decades. Eventually, possibly. I think it's a bad bet to sort of bet against theory, right? The whole point of theoretical computer science is like, if you get an asymptotic advantage, then eventually it's going to win, right? But the trouble is just that eventually could be a long time. Okay, so I would not basically, if you look at the recent calculations that have been done by Matthias Treuer and others, they look like the physical requirements to actually get a speed up using Grover's algorithm looks scary, absolutely scary. It look like you would need a problem involving many quadrillions of possible solutions before you had a hope. So I would say either there has to be a revolutionary advance in quantum error correction that would reduce the overhead for it, and that would make Grover's algorithm more practical, or else, we're not going to see an advantage with Grover's algorithm for many decades. But eventually, possibly, yes, we will see it.
Do you mind if I follow up with a sort of related question? So, what is your opinion on the sort of variational hybrid classical quantum algorithms? Do you think that they're actually useful, or are they just sort of an excuse to hype up the field?
Yeah. So first of all, I don't like the term hybrid quantum classical algorithm, because people, make a big deal out of it. But in reality, every quantum algorithm is a hybrid quantum classical algorithm, right? For every, realistic use of a quantum computer in any foreseeable future, you are going to be using a classical computer, to control the quantum computer, right? And the classical computer will be doing anything that it can do, and the quantum computer will only be doing those things that it has to do, right? Because, to use a quantum computer to do classical computation, is sort of like using the space shuttle to drive around the parking lot, right? It's like, even if it can be done, it is just, it's ridiculously wasteful. Okay, and millions of times slower. So now regarding variational algorithms, I think that from what I can see, they show some promise for problems that themselves involve quantum mechanics. So for quantum chemistry problems, and there they sort of fall under the broader umbrella perhaps of quantum simulation methods. I think they show promise there. I have not yet seen a convincing case that variational methods are going to lead to speed ups for solving purely classical problems. There has been a lot of effort. Smart people like my former MIT colleague Ed Farhi have worked on this, trying to show that this QAOA, quantum approximate optimization algorithm, could help for optimization problems. But I would say that they failed to find convincing evidence of that. The main results that we have about it are negative results. So it remains an open question. But I have yet to see the case for where it's going to help with classical problems.
Well, thank you for that. So I am afraid my colleagues are telling me that if we go beyond 8, we might get kicked out by the platform. So I think it's better if we call a stop. So I'm going to let Luna say the goodbye.
Sure.
All right, thank you ever so much for your time and joining us from across the pond, especially with your handwritten notes, which I'm sure everyone appreciated. And of course, thank you, Carlos, for mediating the Q&A session that just happened. Thank you goes out to our committee members, as well as everyone joining us in the audience today. Next Monday evening, we'll be hearing from Oxford's own Professor Parrington about how culture transforms the human brain. Enjoy the rest of your evening and hope to see you then. Goodbye.